Brain-computer interfaces, BCIs, a deep dive. Brain-computer interfaces, BCIs, also known as brain-machine interfaces, BMIs, are systems that enable direct communication between the human brain and external devices. These interfaces bypass traditional neuromuscular pathways, translating neural activity into commands for computers, prosthetics, or other electronics. BCIs hold immense promise in both clinical and non-clinical domains, aiming to restore lost functions, augment human abilities, or create new modes of interaction with technology. How BCIs work. At their core, BCIs operate by capturing brain signals, interpreting them, and translating them into actionable outputs. The process involves several key stages. 1. Signal acquisition. This is the process of recording brain activity using various methods. Electroencephalography, EEG, is the most common non-invasive technique, where electrodes are placed on the scalp to detect electrical activity. Invasive methods like electrocorticography, ECOG, or implanted microelectrodes provide more precise data but involve surgical procedures. 2. Signal processing. Raw brain signals are complex and noisy. Algorithms filter and process this data to extract meaningful features, patterns that correspond to thoughts, intentions, or specific mental tasks. 3. Translation algorithms. These features are mapped to specific commands. For instance, imagining moving your right hand might correspond to moving a cursor right on a screen. Machine learning plays a crucial role in refining this mapping, making BCIs more accurate over time. 4. Device output. The interpreted command is then sent to an external device, a robotic limb, computer cursor, or wheelchair, enabling the user to interact with their environment. Applications. Medical use. BCIs were initially developed for clinical applications, especially for individuals with severe motor disabilities such as ALS, amyotrophic lateral sclerosis, spinal cord injuries, or stroke-induced paralysis. BCIs allow these individuals to communicate via typing interfaces, control wheelchairs, or operate robotic limbs. Prosthetics. Advanced BCIs can control robotic arms or exoskeletons, restoring a degree of autonomy. Some systems even provide sensory feedback, giving users the sensation of touch. Neurorehabilitation. BCIs are being tested as tools for rehabilitation, helping retrain the brain after injuries like strokes. They can encourage neural plasticity, potentially accelerating recovery. Cognitive enhancement gaming. Beyond medicine, BCIs are expanding into consumer tech. Companies like Neuralink envision integrating BCIs into daily life for memory enhancement, direct device control, and immersive virtual reality experiences. Invasive versus non-invasive BCIs. Non-invasive BCIs. These use external sensors and are safer but less accurate. EEG caps are lightweight and affordable, but suffer from low signal resolution due to interference from the skull. Invasive BCIs. These involve implanting electrodes directly into brain tissue, offering high signal fidelity and the potential for more complex tasks. However, they carry surgical risks and long-term biocompatibility concerns. Ethical and social considerations. BCIs raise profound ethical issues. Privacy. Brain data could reveal intimate thoughts or emotions. Who owns and controls this data? Security. BCIs could be vulnerable to hacking or manipulation. Consent and accessibility. Ensuring that users understand the implications and that technologies are accessible, not only for the wealthy or privileged. The future BCI technology is advancing rapidly. Innovations in wireless systems, AI, and brain mapping are pushing the boundaries of what BCIs can achieve. Companies like Neuralink, Synchron, and academic institutions worldwide are working towards scalable, minimally invasive interfaces. In the long term, BCIs could enable neural augmentation, allowing humans to interact with machines at the speed of thought, connect minds across networks, or even achieve forms of synthetic telepathy. Though many technical and ethical challenges remain, the trajectory of brain-computer interfaces suggests a future where the lines between thought, technology, and action continue to blur, transforming how we live, communicate, and understand consciousness itself.